Okay, let's solve our problem numerically here. So I've got my spreadsheet up. I need to put some labels in. I'll put in a T, a P. We need our slope, which is our delta P over delta T, and that from our formula is just P, so we have that. Okay, so I better make that just a little bit wider, and let's see, so then I need my slope times delta t, so m, I guess I'll use an asterisk times delta t. Okay, so we have that. Probably I should put a delta t in here somewhere just in case I want to change it. You know, so I could do something like delta t equals, and then here we're starting off with 0.1. That's what we did graphically. Now again, I can make some things look a little better, probably centering all these things. We'll make that look a little nicer. Maybe putting this over to the right and this one over to the left, and we have that. So I'm making this video. When it will go on to the internet, not real sure. We had a lightning strike a little earlier this afternoon that well, when it hit, I felt like it hit next to me, you know, in this chair, and so our modem has appeared to have been fried, but we're waiting to see. It'll be a couple days before we know, I think. Okay, but anyway, back to this. So we have t. Now what we know is that t starts at 0 and p starts at 1 for our problem. Then what we also know is this formula that our slope that we're looking at, or our rate of change of p with respect to t, is just p, and so we'll put that in there. Now I don't want to put a 1. I want to put whatever's here under the p at the time. So I say equals, and then I click the B2 and hit enter, and so that says 1. And then here it's just this slope times my delta t. Now in this case with the delta t, I need a $sign in front of that 1, because as I copy down, I always want to look at that cell. I don't want to look at the next one down and so forth. So that's a absolute address. Now I could put a $sign there as well. Doesn't really matter because I'm not moving side to side, but I do that. There's my 0.1 times the 1, and then here, right, to go up, I take the previous value of t and I add my delta t to it, and again I need that $sign. And again, if I wish, I could put 1 in front of the f, but I'm not going to worry about it this time. So there's a formula for that. And then p, well, p was, remember that this is the point slope idea, and so p, the new value of p at 0.1 along that straight line, is the old value plus the change, which is the slope times delta t, and so I'll click there. And sure enough, 1.1, yep, that's where I got to. Now this this formula is just B2, and so at that point I can just pull that down or do a copy paste and all that, so that's good. And then the same thing here, this formula is fine. So at this point all these formulas are ready, that every other row should have the same formula in it. So I pull these down, I get to there's 0.9. Oh, that's kind of cool. Christmas tree farm or something. And I get to 1, and I see that I end up here with my solution, 2.5937. I believe if you recall from our graphical solution, the graphical solution, which in essence did this same thing, we could have made this same table within Desmos, but it's much easier to see here. But I believe we had an answer of 2.5937, so we have that same answer, because in fact really we're doing the same process. Here though, tabularly, we're only getting the value at particular points, whereas when we did it graphically we got that nice curve. And we could kind of simulate that by inserting a chart here. So for instance, if I just to show, we can get a very similar picture here. If I highlight that, insert a chart, make it a scatter plot, not a line graph. There's pretty much never a case where it makes sense to use a line graph. Now, so here's my XY scatter. So that's the chart type. I've got my series all set. Now, chart elements, I'm not going to mess with that right now. But if I want it to look like what I had before, I could choose the lines only and get that picture. We can't see it, it's behind us, but now given I'm making it from the points, I would say a better choice, if you were to use a plot like this, I would say this is probably the better choice in this case, because I'm actually making this from these points and then filling in straight lines between it. So I can finish, and there's a very similar picture to what we had using Desmos. And again, finishing out at 2.5937. Okay, now, but I'm going to get rid of that. I don't really feel I needed it at this point. So I'll click there, hit backspace or delete, and so here I have my solution. Now what's nice is in this tabular case, remember that our answer is supposed to be e to the x. And so suppose I squeeze that in inside here. Now, it's probably easier to put it in this column. This is what we're doing, and that's good. But just so you can see, what you might compare it to, so I'll insert columns left. Here is my e to the x. So there's e to the x, and so I'll say equals. Now, in most spreadsheets, to get e to the x, you say the exponentiation function, exp, and the number here is 0. And of course, they're perfect there. By the time I get to here, they're off by quite a bit, right? Almost, or a little over 0.1, just like we were on the graph. But again, what we can see is by changing delta t and making it smaller, we can make this error smaller. So we'll have to pull this down, copy things down a ways, but let me make it 0.05. Okay, now see, we're only going to 0.5, but if I grab this, and the nice part here is this is very quick to update. And so you see now, notice at 1, I'm at 2.65 instead of 2.59. So I'm closer to that 2.71828 number that I should have. Okay, and we can take it down really small, take it down to 0.01, and pull this down. So we have to go down a ways to somewhere around 100. So there's 1.04. I'll drag it back up here, whoops, to 1. And notice we're really close. We're getting there. We're within 0.1, about, well, less than 0.014. Okay, so if I made this smaller yet and drug this down more, I could make it even closer. But so you see, it's really just a matter of how small I want to make that delta t, and as delta t gets really, really close to 0, we get closer and closer to this exact continuous solution of e to the x. Okay, but that's all there is to making the tabular case. What we could do is ask the question, what does delta t need to be to say get it within, right at about 10%. Well, what is 10%? Well, I've got a calculator, all right? So I could look at 10% and say, well, okay, I want to take 0.1 times e to the 1. And no surprise, that's just 0.2718. And then if I take my e to the 1 and I subtract off that 10%, the question is, well, what's it take to get within 10%? Oh, not much, all right? 2.44, I did better than that when delta t was 0.1. Okay, so delta t could be bigger than 0.1 to get within 10%. Well, what if I wanted to be within 1%? Then I have to get to 2.69, and here I'm better than that. So again, to get within 1% at 1, I would need to be something a little bit bigger than 0.01. And if I wanted to get to 0.1%, 2.7155, and this was not at 2.71 yet, so I would need something a little smaller yet than the 0.01. But you see, I can check that very quickly with technology. What does my delta t have to be to get close enough here? And again, I can do that here because I know what the right answer is. If I didn't know what the right answer is, I would have to use some other techniques to kind of guarantee how close I was. And those are, you're still using calculus and all that to do it, but it's just farther along. You have to learn a few things first before you can do that. So here we have the actual answer, but we could do something similar to this even if we didn't have the actual answer. Okay, so not too much in the way of steps to do this numerically, to get a table. And again, if I want to enter a table into, well, I'm not going to do it, I guess, here, but into a Word type document, right? I can just highlight what I need, whatever that is, and copy it, paste it into the Word document. And again, if I need to add grid lines and so forth, I go find something like this to add borders. And so the tabular part of doing this, or the numerical aspect of doing this, really not bad. I mean, this is pretty straightforward, and wow, is it easy to add on to it with the copy and paste sort of fill in kind of thing. So you know, I like this, doing it this way numerically, and then once I have it numerically, I can generate a nice graphical picture, which is nice. So so there you go. I think that does it, and then some, as to how we would do this numerical approach.